you should know, based on other work with extraneous roots, when we had radical equations, there were extraneous roots. An extraneous root is a solution to an equation that you get legitimately following the rules of math, but it just doesn't work. And I will tell you right now, with these types of equations, the only real extraneous roots you will get, the only answers you will get that aren't actually answers are non-permissible values. Okay? So if I look at, I'm going to go to one of the simpler ones. If I look at this equation, I hope you can see in this equation, and we can jump ahead to it, that x minus 2 is not allowed to be 0. Why? Well, because x minus 2 is a denominator. Okay, and 2x minus 1 is not allowed to be 0. And again, just like I've said before with things like this is pretty easy, this part. I mean, you just solve each of these. This turns into x is not allowed to be 2. This turns into x is not allowed to be 1/2. I feel as though at this stage of the game, I shouldn't need to explain how to rearrange 2x minus 1 is not equal to 0 to get x is not equal to 1/2. Okay? But what if, I'm talking about extraneous roots here, what if when we solve this equation, one of the solutions is 2? I don't know that it's going to be. But what if we do the work here and manipulate this equation and rearrange it and solve it for x, and one of the solutions is 2? Well, but the original equation, x is not allowed to be 2. So that would be an extraneous root. It's a little bit different than absolute value equations or square root equations in that you don't really have to do much looking. You just say, did I get an answer that's on this list? And if I did, I throw that answer out. That's it. So, solve and check for extraneous roots. What I've done, because this can be quite challenging for some students, is I've put notes for example 1 and 2 that in your textbook there's a similar example to number 1. Okay. So let me rewrite this. Well, I'm not going to rewrite it just yet. We will rewrite it together in a minute. What makes this equation difficult to solve? I want everybody to think about that. Why is this equation an equation that you don't already know how to solve? Why don't I just say, well, geez, come on, solve this. You guys know how to solve this. What's different? What's the problem? Charlie. You mean the fact that it's z instead of x?
No.
There are denominators, right? There are denominators. If there are square roots, we would like to get rid of square roots. If there are absolute value signs, we would like to get rid of absolute value signs. If there are denominators, we would much rather not work with fractions. So I'm going to rewrite this spaced out a lot, but what should we do as we rewrite it? There's something we need to do. Factor. Remember? Factor. Everything about rational expressions is about factoring. So I'm going to factor this into 2 over z plus 2, z minus 2. That should be a piece of cake. I'm going to leave some space there. How much space you leave depends on how neatly and small you can write things. Okay? And then I have 10 over 6 times z plus 2. And then I'm going to leave some space, and I have equals 1 over z minus 2. And we want to get rid of those denominators. How can I get rid of this denominator of z minus 2? I mean, I could just erase it, but I think you know by now that's not what I'm talking about. What can I do to this equation to get rid of the z minus 2? Multiply? Multiply what by z minus 2, Ashira? Oh, that's the best answer you can come up with. Everything. Multiply everything. I don't mean multiply z by x, z minus 2, and 2 by z. You know what I mean, right? Multiply both sides of the equation by z minus 2. So I'm going to do that. Now, that will get rid of this z minus 2 that I'm pointing at here. It will even get rid of this z minus 2 over here, but I will still have denominators. So what can I do to everything to get rid of the z plus 2? Multiply everything by z plus 2, meaning every term or both sides of the equation. And that's great. That is going to get rid of the z plus 2 and the z minus 2 in this expression. It's going to get rid of the z plus 2 in this expression and the z minus 2 in the third expression. But I still have something else in the denominator. I have a 6. Well, I'm going to multiply everything by 6. And it doesn't matter the order that I multiply these in. And I've run out of room here on the right-hand side, so I'm just going to put the 6 here. It doesn't matter the order that I multiply things in. So what happens, and you need to be very careful and organized in your thought here. This entire thing is a single rational expression. And we can simplify a single rational expression by canceling common factors. By the way, I hope that you can appreciate that this is the lowest common denominator. And you know, I can tell you we have to multiply both sides of the equation by the lowest common denominator. I like thinking this way, though. Let's multiply by whatever we need to get rid of the denominators. Notice if we're adding rational expressions, you keep the denominators and you convert everything to fractions with that denominator. Here, we're getting rid of the denominators. In the middle term, which is also a single rational expression, as is this term on the right-hand side, we can cancel within a single rational expression any common factors. So the 6 is gone, the z plus 2 is gone, the z minus 2 is gone, and here's where you just have to be careful. All the denominators are gone. We're just going to rewrite whatever we have left. But you have to be careful not to miss anything. The only thing I have left over here is 12 plus, what do I have left here? 10 times z minus 2 equals 6 times z plus 2. And we'll finish the question in just a minute, but I regret using z here in 2's. Don't confuse the two. But I want to make a point that this is a grade 8 equation. It's not even going to be quadratic. There's not going to be any z squareds. So we've simplified things from a grade 11 question to a junior high question. I multiply that 10 through. I multiply that 6 through. I can see that I have a larger balance of z's on the right or the left-hand side, so I'm going to move my z's to the left-hand side by subtracting 6z, giving me 4z, and I'm going to collect my numbers on the right-hand side. I have 12. I have to add 20 to get 32, and I subtract 12 and get 20. Z is equal to 5. Now, is 5 allowed? We go back to the original equation. We probably want to look at it in factored form. And I'm looking at all of these factors. And I'm saying, is 5 permissible? Yes. The only non-permissible values are 2 and negative 2. So 5 is allowed and 5 is the answer. I want to show you the big picture here now and ask if anybody has any questions. about, in particular, is there something else we could have done that maybe would have made our job a little bit easier? And the thing that I'm talking about is something that sometimes you have to do, otherwise the job is impossibly hard. Ashira. What do you mean? Can you be very specific about, you're talking about this middle highlighted term? What do you mean specifically I could write?
Like before that, you could factor out x from the numerator.
Right. And I could do that here as well. The point that Ashira is talking about is that this 10 over this 6 can be reduced to 5 over 3. And I could have done that then, and then had a 3 down here and not multiplied everything by 6 but by 3 instead. You will notice that at this point right here, everything is divisible by 2. 12 is divisible by 2. 10 is divisible by 2. 6 is divisible by 2. Everything is twice as big as it needed to be. So if you happen to be able to reduce something first and you catch it, try it. All right, let's move on. Let's take a look at the second example. Let's rewrite this with space and in factored form. 3x. I just want to check something actually. It did say check for extraneous roots. It never really says what are the non-permissible values. I have 3x over x plus 2. And then minus, leave some room, minus 5 over x minus 3. Leave some room, x equals rather negative 25 over, and we factor this. And this is a pleasant surprise. It factors into x minus 3, x plus 2. So this is how I used to teach it years ago. I just say, look, if you have a rational equation, you need to multiply both sides of the equation by the lowest common denominator. Step one. And I've grown as a teacher. I never used to really explain to students why that's the case. I assumed you would figure it out. But what we're doing is we're multiplying both sides of this equation by x plus 2, x minus 3, which, yes, happens to be the lowest common denominator. But that's not my motivation. I'm multiplying by those two things because those are the two things that will clear out the denominators. When we're adding or subtracting, we're converting to those common denominators so we can add the fractions together. Here we're using the common denominator to clear the denominators. So what happens, let me just put some brackets around this stuff. What happens is the x plus 2's cancel here, the x minus 3's cancel there, and everything cancels here except for the negative 25. I have a question for you. When I rewrite this, well, let me rewrite it. Let's rewrite it. 3x times x minus 3 minus 5 times x plus 2 equals negative 25. Are you with me on that move? Okay. My question to you is, how many of you would have maybe just written the next line first? How many of you would have done this and continued? Okay. Just be careful because you're going to look at this and you're going to say this is 5x plus 10, right? And it is. Just make sure you don't do this. What's that? that negative 5, that negative is owned by the 5. When we multiply that 5 through, it's negative 5 that gets multiplied through. And I'm going to erase this just to narrate my train of thought here. When I multiply this out, this is how I would describe it to a student. I would say 3x times x, 3x times negative 3, negative 5 times x, and negative 5 times 2. It's the equivalent of forgetting the brackets, right? That negative needs to be tied to the 10 as well. And this is equal to negative 25. I just want to double check my work there. I think we're okay. 3x squared minus 9x minus 5x minus 10 equals negative 25. Now, unfortunately, this is not a grade 8 equation because it's a quadratic equation, but that's okay. We still know how to solve this. This is 3x squared minus 14x plus 15 equals 0. I add 25 to both sides and get 15. I need everybody to determine if that's factorable. You're going to do the b squared minus 4ac trick. Or if you're really good at factoring and you can see that it's factorable, I'm not that guy. Go ahead and factor it. But let's find out if it's factorable first. For most of us, we have to do this. B squared. Of course, I don't worry about the negative with the 14 because I'm going to square it. Minus 4 times 3 times 15. It's factorable because 16 is a perfect square. Okay, this isn't going to be too bad. 3x and x. I'm going under the assumption that it's 3 and 5. I'll bet you could go through all of your formal math education, including calculus, and never come upon a quadratic that ends in 15 where it's 15 and 1 in the factors. I mean, maybe it's going to happen, but it's very rare. If it is 3 and 5, the 3 cannot go with the 3. It has to go away from the 3. Let's see. These would have to both be negative, wouldn't they? To multiply to give positive 15. And just do a check here. Do they combine the outer and inner products? Your first will give you the 3x squared. Your last will give you the 15. Do the outer and inner products add together to give negative 14x? Okay, so it's factored correctly, which means that 3x minus 5 is equal to 0, or x minus 3 is equal to 0. Rearranging this, I think you might show one step on a written response of writing 3x equals 5. But just between you and I in teaching and learning mode, we rearrange that. Are we okay with that? And x equals 3, we're okay with that. Before we move on, any questions with example B? Really? No problems? Seriously? Come on. Nate?
How do we know which ones would be the extraneous three?
Oh, I don't know. Are there extraneous roots? Let's start with that. Which of these numbers is extraneous? I mean, not every equation that turns into a quadratic is going to have extraneous roots. But there is, I think, an extraneous root here. What is it? X is equal to 3. We can't use this. That doesn't mean X, it just means no. Why? Excellent. Because when we look at the original expression, whether we look up there or we look at this line, but we look at the brown stuff, there are non-permissible values of 3 and negative 2. And we got 3 as an answer. So it's not a solution. Excellent. All right. Final example, C. Well, I've already got the non-permissible values over here, so if we happen to stumble upon them in an answer, we know that we have to throw them out. They're not valid. I'm going to rewrite this. We're winding down in the lesson because, quite frankly, there's nothing even to factor here. Okay? But I'm going to rewrite this with a little bit of space. And I'm going to clear this out. You have, I think, I'm assuming, you guys usually have more room on paper than I have up here, don't you? Okay. So everything's already factored. I'm going to have to multiply the top and the bottom. Whoops. No, I'm not going to multiply the top and the bottom. I'm going to multiply the left side and the right side by 2x minus 1 so that I can get rid of the 2x minus 1 in the denominator. I could have been more generous with my spacing here. I also need to multiply both sides of the equation by x minus 2. Again, this is about motivation. What's your motivation? Why are you doing this? You're doing it to get rid of denominators because denominators make things more difficult in mathematics. The 2x minus 1's cancel. The x minus 2's cancel. We're left with 12 times x minus 2 equals 2 times 2x minus 1 minus 5 times 2x minus 1 times x minus 2. It's funny because I said, well, we're starting to wind down. This is not maybe going to be as simple from here to the end as I thought it would be. Got a bit of work to do here. I know you know this. I hope you know this. But I want to make sure. This final term in the equation, 5 times 2x minus 1 times x minus 2, is really just the product of three things. We have to multiply it out. When you multiply out three things, you multiply any two of them and then multiply by the third. So 2 times 3 times 4 is 24. Because 2 times 3 is 6. 6 times 4 is 24. Or 3 times 4 is 12. 12 times 2 is 24. And my recommendation is I would FOIL this out first. I wouldn't multiply the 5 into one of these because then you're dealing with bigger numbers in the foiling. So I would multiply that out first. All right. 12x minus 24 equals 4x minus 2 minus 5 times, I'm going to get a 2x squared minus 4x minus 1x plus 2. And I want us to just stop, take a breath, and double check all of our work here. It looks okay to me, but it wouldn't be the first time that I've said that and still had a mistake. What do you think? Okay. So let's continue. Let's multiply that 5 in. 12x minus 24 equals 4x minus 2 minus 10, not equals, minus 10x squared. I think we can handle the fact that this is negative 5x. We don't need to rewrite it and put negative 5x. So negative 5 times negative 5x is 25x squared. And then negative 5 times 2 is negative 10. It's not negative 25x squared. I apologize. It's negative 25x. Okay, I'm really glad, and I've never mentioned this to this class before, but I'll mention it now. I'm glad that you guys are attentive during the lesson, and I don't just mean well-behaved. That's not my point. My point is I can see that you're looking at this and you're doing the math yourself. You're double-checking things. You're not just blindly writing down what I'm writing down. So we're okay with that line? Okay, it's quadratic, so off we go to quadratic equations where we zero the equation. I'm going to move the x squareds to the left side where they become positive. A lot of x's to keep track of here. I have 4 plus 25 is 29. I'm going to take the 12x minus the 29x. How's my arithmetic there? I don't know why that's stumping me. And then I have minus 24, and on the right side, I've got negative 12. I've got the negative 2 and the negative 10 is negative 12. So I'm going to add 12 to negative 24 and get negative 12. "62 eyes are better than 2. Take a look at it, make sure you're in agreement. I'd be surprised if this is factorable. I don't know, just looking at the numbers. I'm glad to see that you're grabbing your calculators and determining if it is. If it isn't, it's not the end of the world. That looks like a perfect square to me. Or am I just deceived into thinking because it ends in a 9? Yep. Thank you. Saying this should be a 2. Okay. Oh, that looks even more like a perfect square. Is that a perfect square? No? I guess every time I see the number 9, I think perfect square. Oh, well, you know, as I said, it's not the end of the world. We do have, hello, old friend, our quadratic formula. And in fact, we already have a lot of the work done to get an answer because we know, was it 769? Okay. So our solutions are x equals negative b plus or minus root 769 all over 2a, which is 20. Now, both of those answers, 17 plus root 769 all over 20 and 17 minus root 769 all over 20, they're both valid because when you look at the original equation, the non-permissible values were 2.5 rational numbers. The other thing I want to point out is that I think 9 probably divides into 769 without remainder. I suspect. Can you let me? It doesn't. Okay. Well, maybe that's good, but my point was going to be even if it does, I don't really feel like extracting that 9 out and writing the 3 outside because 17 is a prime number. I'm not going to be able to factor anything out to cancel with something in the 20. 769 might even be prime. Is it divisible by 3? No. I think it's probably prime. Anyway, that's it. The big difference is when you're adding or subtracting rational expressions, which is what we spent 2 days last week doing, you convert everything to the lowest common denominator. You keep the denominators. Here, our whole goal in all 3 of these, look at the first example. We went from this, that's all in blue, to the line below, no denominators. B, we went from this, which is in brown, to the next line, no denominators. No denominators. You're always following the Paul Way school or philosophy of mathematics. You're trying to make things into something you could have done last week or the week before or last year or 2 years before. So your goal is to eliminate the denominators on page 348, 2, 3, 4, and 6. We actually only have one lesson left, which we're going to cover tomorrow. If I stick to the 2 days of review and then exam, our exam is Monday. But I'm going to have 3 days for review here because particularly when we get to tomorrow's topic, things can get pretty dicey. We're going to need lots of review. Okay? And there's lots of practice we can do. So get to work on those, please. You still have about 15 to 20 minutes left. I will come around and give you a hand in a minute or two. Yes, of course.